it's just turbulent flow.
Upstream of the plate, and because the circulation per unit length along it is constant, you conclude that all of the vorticity influence.
Right. We'll skip to the next one.
So it's quite different.
Oh no, here we are again.
Boundary layers, thin layers of fluid in which viscosity and
Here we go.
flow dynamics are formed along the surfaces of the object. Behavior of these boundary layers under the influence of pressure gradients can, in some cases, drastically alter the flow. This streamline pattern is very nearly what one would predict from inviscid flow theory. Because the Reynolds number is large, influences of viscosity are confined
Oh, there it is. That's the one I want.
to the surface of the wing.
Okay, we're going to skip ahead to here.
First, the case of a decreasing pressure.
Don't you wish I talked like that?
In the flow
He should fire his editor. His words don't match his mouth.
This is way 1950s. That's how people talked in the 1950s. That's how lecturers, professors professed during the 1950s.
And you wonder why there was the 60s.
All right, so here's a new experiment. And now, and this is showing, okay, you've got the same thing going on. You're making your hydrogen bubbles. And here you have a fairly wide thing, so it's moving slowly. And then it gets thinner down here, so it's got to move faster because you've got the same amount of fluid going through a smaller area. And you can see, look at this, the wave stays together for longer, doesn't it? Look at how. So, all right, stop. Okay. Here, where it's higher velocity, the boundary layer is thicker. Look, you can see the boundary layer here is about that thick. Can everybody see that? Mm-hmm. And then here, it's much, much thinner. So, more shear stress here. Higher velocity, steeper gradient of the boundary. And it's the steepness of the boundary layer gradient. How close to the bottom is the water moving fast that causes the drag. If the water is moving really fast close to the bottom, you get lots of drag.
So it's that angle you're referencing, the one literally on each one of those lines, there's a different angle.
And then the magnitude of the change.
Okay.
Downstream is about half what it is upstream because the two-dimensional flow contracts 2 to 1.
Yes. All right.
In the contraction, the effect of the pressure gradient in the boundary layer is to enhance the already high shear stress or vorticity configuration very near the wall. It is as though a boundary layer were being generated within the old. Boundary layer. So velocity gradient and shear stress are less, and the boundary layer is thicker. In the reverse,
here we go.
Flow.
This is what I wanted to show.
The boundary layer is said to have separated.
Okay, here's flow separation where we were talking. See the
Point on the wall where the fluid in the upstream boundary layer meets the fluid from the region of flow reverse is called
faster velocity to slower velocity. Or a wider channel.
Yeah, where it goes wider, here the flow is separating. So it's cruising along, and the main flow keeps going straight, and the rest kind of loops back, makes what we call an eddy.
Mm-hmm. Or tidal pools, right? Yeah.
Tidal pools.
Like on the sides of the current in the river, you get nice little
back eddies in rivers. Every natural current is full of these things. And the most fundamental one, and the reason we deal with it,
like a Schlitterbahn where the tube gets stuck. It's the same thing.
On a big sand dune, the wind blows up the back of the dune, and then the wind keeps going over the top. And some of the wind loops back and makes a big eddy on the front of the dune. So sand is blown over the top of the dune and then swept up so it accumulates on the front of the dune. Dunes, this is why dunes and ripples form like they do, is this flow separation that allows, that erodes sediment from the backside and causes the deposition of sediment on the lee side, the side where there's flow separation. Okay? All right, we'll do a little video of that, and then I'm going to see if I can't find the one that.
Separation of the laminar boundary layer is near the first line.
Ah, there we go. Okay, it's the next one. So I wish I could fast forward. But it's here. There we go. Okay.
A film with a high-speed camera can show the stages in transition of the boundary layer from a laminar one to a turbulent one.
Okay, there are two, so far we've talked about laminar boundary layers. There are two types of boundary layers. The first is the laminar, where you have smooth sheets of water sliding past each other. And the next is turbulent, because once this gets far enough away from the material, and once it's going fast enough, you can imagine you're a pocket of water moving along, and the stuff below you is going slower. You're going faster, and then you tumble over head over heels because the material below you is not going fast enough. And so the water does that.
And that's not an eddy?
It is. But this is a smaller scale turbulent eddy. And turbulence creates all sorts of eddies and other confusion. But it basically is, and we'll actually see, it creates eddies, it creates streaks, it creates bursts, different things like that. But what it is the water basically tumbling over, and you can see what that does is it brings higher velocity water down closer to the surface. So down, and it makes that boundary layer get flatter and increases the shear stress. The higher the shear stress, the flatter the boundary layer is, and the more you have high velocity turbulence down near the surface.
Can you say that last part again? The last part?
The higher the shear stress, the more resistance to flow, the flatter, the thinner the boundary layer is, and the more turbulent it is. The more that you're bringing that high velocity water down closer to the sediment surface. And this shows the transition from laminar to turbulent flow. I think there's one here where they actually have a metal plate where like one side stays turbulent and the other side gets, and so here you can see.
Adverse pressure gradient causes transition to occur within the field of view.
Okay. Here we go. This will be.
Effects in the transition are very complicated and interdependent.
So here comes this is now the blowing smoke.
Nearly two-dimensional wave, the Tomain shifting wave, followed by the appearance and growth of three-dimensional disturbances associated with streamlined vorticity. Then turbulent spots can be seen. And finally, fully turbulent flow appears. Here, the exact position where growth of two-dimensional disturbances begins depends on random small-scale fluctuations in the flow, and therefore varies with time in a random way.
See how those nice smooth things are now breaking up?
This boundary layer around the channel bend is made turbulent by placing an obstruction in the layer upstream.
Oh, good. Here we go.
The obstruction stimulates the naturally occurring processes and hastens the onset of transition.
So you
The
just
flow
put it.
here is all downstream.
I can't see anything. It's all
The
smoky.
results in separation and backflow.
Yeah.
Bubbles accumulate at the separation point.
All right, let's skip to, oh, there we go. It's the next, it's coming up real quick.
Bottom boundary layer turbulent finds in this diffuser, which was used before, some boundary layer turbulent by inserting a drift rod upstream.
Oh, okay, here we go.
The boundary layer is able to withstand the adverse pressure gradient in the diffuser.
Okay. Laminar flow, turbulent flow. And what's happening here is this stuff is going down like that.
You said that happens because it's going faster, right?
Because this is going fast and this is going slow, and when that gradient gets to be too much, the water tumbles over itself and creates what we call turbulence. And you can see the turbulence starts off near the boundary, and once you've started that, it'll gradually grow up in and encompass the entire flow. You're looking confused.
No, I was just wondering if, like, let's say we're introducing, like, cold saline water into fresh water, warmer fresh water. That's going to be more exaggerated, right?
Yes, and you can actually have, if you have two different fluids, like air and water, you can generate the same turbulence as the flow of wind over water.
Like the ocean.
Waves in the ocean are created by turbulent flow of wind over water. That's what makes waves in the ocean.
That's why they're really big in the deep ocean. Oh, I said that's why they're really big in the deep ocean.
And that's why they're really big when you have storms, because you have high winds. Anyway, so just check this out for a couple of minutes, and then we'll talk about how the turbulence how the turbulence develops.
The laminar layer along the top wall is separated, allowing reverse flow.
See, now it's starting here to separate there. But notice that that one is smoother, much less turbulence.
These timelines show that in the turbulent boundary layer, there is no separation. Overall flow is downstream.
And here you can see that turbulence. It's not separating, it's just tumbling.
To see why a turbulent boundary layer can withstand a larger unfavorable pressure gradient without separating, we shall again examine the flow along a flat plate.
Let's not go, oh, there we go. Huh?
How many times faster does it need to be to create
What?
how many times faster does the alkaline need to be to create a turbulent?
Ah, that's the next good question. Yeah, first, let's stop there. So, how do you know when wind flow is going to be turbulent or laminar? Well, there was a guy named Reynolds, who's a very famous physicist, who decided he'd do it, and he couldn't calculate it, so he got a whole bunch of pipes of different material and did the roughness, and calculated shear stress, and then he pushed fluid down the pipes at different velocities, and he just did thousands and thousands and thousands of experiments. And he discovered there is, let me see, let me go to the PowerPoint. He came up with an equation that related what are called the inertial forces, the density of the fluid, the depth of the fluid, and the velocity of the fluid. Though the higher the density, the heavier the fluid, the higher the thicker the fluid, and the faster it's flowing, the more likely it is to be turbulent. So turbulence is increased by these, and what resists turbulence is viscosity. And so he came up with this ratio and created what's called the Reynolds number. And there are 30 different types of Reynolds numbers describing different types of flow over and around different things. But this is the basic Reynolds number. And the thing about it is with turbulence, you saw he was saying that it's sort of random and things you can't measure that change things. Fluid flow is, you enter the realm of chaos, the butterfly effect for weather kind of thing, where small things you can't measure change your result. And so you can run the experiment 50 times, and 30 times it goes one way, and 20 times or 10 times it goes the other. And it's due to random effects you can't see. And so it's chaos. That's what chaos is where you get different results from the same experiment. Is that still big in, when I was back,
Chaos theory?
20 years ago, 30 years ago, that was a huge, people thought chaos was going to explain a ton of stuff, huh? Chaos theory, yeah. Anyway, Reynolds number is chaos theory. And so what he found was that when the Reynolds number is smaller than 400, you have laminar flow.
It says 500 in your handout.
Okay, 500. 500.
Good looking out,
Reynolds
Kagan.
number is greater than 1,000. I think, no, it's 2,000. 2,000, yeah, 2,000. When Reynolds number is greater than 2,000, you have turbulent flow. When it's in between, it's random. If you have Reynolds number of 1,000, sometimes it's turbulent and sometimes it's laminar. And you can't really tell. And it can change. It can cruise as laminar for a while and then become turbulent. And so this is the third big equation we have. So now we have subcritical flow, supercritical flow, turbulent flow, and laminar flow. And very, very few natural flows are laminar. In nature, almost everything is turbulent. And we'll show you why. Let's pretend we've got a river. Our river is very shallow. It's flowing at, it's half a meter deep, and it's flowing very, very slowly at a meter a second. That's 1,001, 1,002. So what is the Reynolds number? This here is a constant. I gave it to you in the first place. It's, I believe, 1.06 times 10 to the minus third.
Mm-hmm.
So give me the Reynolds number for a river with a depth of 0.5 meters and a velocity of 1 meter a second. What's rho here going to be? 1,000. Okay? And this will be 1.06 times 10 to the minus third.
1.06 to the minus what?
10 to the minus 3. 0.00106. You want to do it without having to deal with that.
Yeah.
Pretty much the same thing. Mm-hmm.
So with this very slow, very shallow stream, what's the Reynolds number? Somebody?
About 4.7 to 10 to the 5th.
That's right. Yeah. 470,000. Is that what you guys are getting? Okay.
Mm-hmm.
Icky. Okay. Yeah, so 470,000. So how at a meter a second, here's one thing, how shallow does the flow have to be laminar? To be at 500. I won't make you guys do that. But if I'm looking for the depth at which that's 500. Okay, 500 times 0.00106 is 0.5. We'll round because I don't have a calculator. All right? Huh? Can't be 53. That would be way too. Oh, that 500
0.53.
times 0.00106 is 53?
0.53.
Oh, 0.53, yeah, 0.5.
Yeah.
0.53 divided by 1,000, right? .00053. And that equals, and then divided by 1 doesn't change anything. So are we taking care of everything? So that gives us H equals 0.00053 at a meter a second. Laminar flow occurs at a thickness 0.00053 meters, or half a millimeter. So really, really thin flows. And so about the only places in nature where you get laminar flows are either where you increased the viscosity a whole ton, mud flows. Mud flows are often laminar because the viscosity is so high and the velocity is so low because they're just kind of oozing along. So you get laminar flow in mud flows, debris flows, and you get laminar flow in swamps in 10-centimeter deep swamps where the water's just barely moving along. And that's about it. Okay, questions? How are we doing for time? Oh, shoot.